Now that we have a basic understanding of pressure and how it varies with altitude, let's look at wind. In the simplest sense, wind is simply horizontal air movement. But what causes it? Well, last week we looked at how variations in insolation, incoming solar radiation, caused by variations in latitude, can impact temperature. We will now see that these temperature differences drive the wind. So in a nutshell, this is how it works. Unequal heating of the Earth causes temperature differences on Earth, which cause pressure differences, which create wind. So pressure differences create wind, but those pressure differences ultimately result from the unequal heating of the Earth. Generally, wind flows from high pressure to low pressure, just like water flows from high pressure to low pressure. When an air mass heats up, it expands, and thus it is less dense than the surrounding air, and it rises. As we learned in the previous video clip, that rising air leads to low pressure, and wind blows from high pressure to low pressure. So in this example, wind would be flowing in towards where that region had the rising air. On the other hand, as an air mass cools, it contracts. Thus it is more dense than the surrounding air, and it descends. As we learned in the previous video clip, that descending air leads to high pressure. And wind, like water, flows from high pressure to low pressure, so wind would be flowing outward from that high pressure region. We've covered a lot already in the first 2 minutes of this video clip. I encourage you to pause the video and then go back through it and review these concepts. All right, so we know that pressure differences cause the wind to blow. But we'll see that if we really want to know the direction that the wind's blowing, there are actually 3 factors that affect the direction of wind movement: the pressure gradient, Coriolis effect, and friction. You need to memorize these 3 factors, and we're going to spend the rest of this video clip going through how each of these factors affects wind direction. First, we'll deal with the pressure gradient. As mentioned previously, wind flows from high pressure to low pressure. We call the difference in pressure over a distance a pressure gradient. If there were no other factors present to affect wind direction, wind would simply flow down the pressure gradient, perpendicular to the isobars. We can see that in these diagrams here, wind flowing from high pressure to low pressure. When we have a map with isobars, flowing from high pressure to low pressure, directly perpendicular to the isobars. Notably, though, there are other factors that contribute to wind direction, so we rarely see this flow of wind that's due solely to the pressure gradient. So we sometimes refer to this as just a hypothetical wind direction. Let's see how this hypothetical wind, that depends only on the pressure gradient, would be represented in the diagrams of high and low pressure cells. I encourage you to stop briefly and get out a piece of paper, draw 2 pressure cells, like I've drawn here, 1 high pressure cell and 1 low pressure cell. Label one with an H in the center and the other with an L in the center. And to the left of your drawing, label this as only the pressure gradient, hypothetical. Next, draw 3 or 4 wind arrows on each pressure diagram to demonstrate the wind direction. What would that look like? Well, it would look like wind coming out of a high pressure system. And you can draw more than 1 arrow, and I encourage you to draw several arrows here on your diagram as the wind is going directly out of the high pressure perpendicular to the isobars. In a low pressure system, the arrows are going to be reversed. Wind is flowing from high pressure into the low pressure. So you would draw several arrows perpendicular to the isobars flowing into the low pressure in the center. I encourage you also to put one more label in your diagram. When air is flowing out, we call that divergent flow. So this example here would be divergent flow. When air is flowing inward into a pressure cell, we call that convergent flow. So this example here would be, of the low pressure system, would be convergent flow. Now let's see what those wind directions would look like on a map with isobars. Here we have a high pressure system over Idaho and Montana. You would expect wind to be flowing directly out of that high pressure system. Now this is only hypothetical because we haven't yet considered the fact that the Earth is rotating and there's friction. But for now, it's flowing directly out. On the other hand, down here in Alabama and Georgia, we would expect the wind to be flowing towards that low pressure, coming inward. Now the example we just drew, we said was only hypothetical. It would only be true if the Earth was smooth as a marble, so no friction, and it stopped rotating. But because the Earth rotates, we also need to consider the Coriolis effect. The Coriolis effect is an apparent deflection of free-moving fluids, gases and liquids, to the right in the northern hemisphere and to the left in the southern hemisphere. And this Coriolis effect is caused by the fact that the Earth's rotational speed varies by latitude. The Earth actually rotates faster at the equator than it does at the poles. If this seems strange, consider how far around the Earth must rotate in one day at the equator. That's the entire circumference of the Earth at the equator. Next, consider how far the Earth rotates at the Tropic of Cancer, or the Arctic Circle in that same 24 hours. These circles are much smaller. Thus, in order to cover the greater distance at the equator, the Earth must be rotating faster at the equator. There are many good videos out there on the Coriolis effect, and I've put 3 of them on our website. I encourage you to stop the video right now and go to our website and check out the 3 first videos that I posted. They're on a link right below this video clip on our class website. Okay, hopefully you went and reviewed those videos. If you didn't, I really encourage you to do so. All right, so we know that the Coriolis effect tends to move things to the right in the northern hemisphere, and it makes it look like things are going to the left in the southern hemisphere. We're going to focus on the northern hemisphere. So let's think about that apparent deflection to the right. 2 other important points about the Coriolis effect are that it has a greater effect on faster moving objects. Thus, there's no need for you to adjust the direction you swim as you swim across a pool, for instance. You move too slow. But for rockets and bullets and that sort of thing, the Coriolis effect would have to be taken into account. Also, the Coriolis effect has the strongest effect at the poles and diminishes to 0 at the equator. Let's see how the Coriolis effect plays out in high and low pressure cells. So now you're going to draw 2 more pressure diagrams, 1 high pressure and 1 low pressure, right below the 2 you've already drawn in your notes. We already drew the hypothetical example of only the pressure gradient mattering in the high and low pressure cells. Now we're going to draw what occurs if the pressure gradient force and the Coriolis effect are both taken into account. And we find this condition in the upper atmosphere. So go ahead and draw 2 more cells. First, let's consider a high pressure cell in the northern hemisphere. The pressure gradient moves the air outward perpendicular to the isobars. But now the Coriolis effect is going to pull it to the right. Eventually, the Coriolis effect and the pressure gradient, represented here, the pressure gradient's represented by red and the Coriolis effect by green, eventually they balance out and we end up with what we call geostrophic flow. Again, notice in this diagram the pressure gradient is always moving the air outward, and the Coriolis effect is always trying to pull it to the right. And again, they balance out and we end up with something called geostrophic flow that is just flowing round in circles parallel to the isobars. And you can see around a high pressure cell, this results in clockwise flow. Clockwise geostrophic flow. I would write that right below your pressure diagram. clockwise geostrophic flow. In a low pressure cell, the red arrows here show the pressure gradient pulling the air in, and the green arrows here show the Coriolis effect always moving it to the right. And so the air is coming in, but it gets moved to the right, and they balance out, and we end up with, how would you describe this? Counterclockwise geostrophic flow around a low pressure cell. Sometimes people get confused because it looks like it's going to the left. But remember, the pressure gradient is pulling it in, the Coriolis effect is pulling it to the right, and the result is counterclockwise geostrophic flow. You should write that below your diagram. So in the northern hemisphere, if we consider the pressure gradient and the Coriolis effect around a high pressure cell, we'd end up with clockwise geostrophic flow, and around a low pressure cell, we'd end up with counterclockwise geostrophic flow. In the southern hemisphere, this would be reversed, but I don't want you to focus too much on the southern hemisphere. Just know that it would be reversed. All right, the last factor we need to consider is friction. Friction is present in the lower atmosphere as winds flow over forests, buildings, mountains, etc. And the primary effect of friction is to slow down the wind. Notably, though, when the wind velocity is decreased, the Coriolis effect is also decreased. Thus, for surface winds, the pressure gradient and the Coriolis effect do not balance out, creating geostrophic winds like they do in the upper atmosphere. Instead, the Coriolis effect is diminished and the pressure gradient always wins. So the air comes outward from a high pressure and it curves a little to the right, but it doesn't completely turn to the right. So we end up with divergent clockwise flow. Let's have you draw that by drawing a third pair of pressure diagrams. This time, you're going to have the pressure gradient, the Coriolis effect, and friction, and this models what's going on in the lower atmosphere. The pressure gradient moves the air out, Coriolis effect bends it to the right, but not quite all the way, and we end up with that clockwise divergent flow. Similarly, in a low pressure cell, the pressure gradient is moving the air in, the Coriolis effect is moving the air to the right from the direction of wind movement, and the pressure gradient dominates because the Coriolis effect is diminished due to friction, due to the decrease in the wind speed. So the pressure gradient dominates and the air does have a counterclockwise turn to it, but ultimately it converges in at the center of the cell. So this is called counterclockwise convergent flow. So in the lower atmosphere, in the northern hemisphere, out of a high pressure we have clockwise divergent flow, and into a low pressure system we have counterclockwise convergent flow. You should have now drawn 6 diagrams, and you can compare your diagrams to those drawn here. You have a high and low pressure diagram when we're only considering the pressure gradient, which is just hypothetical. You have 2 diagrams, one for high and one for low when we're considering the pressure gradient and the Coriolis effect. That would be the case in the upper atmosphere. And in both cases, we end up with geostrophic winds. And then you have the case in the lower atmosphere. We have to take friction into account. And friction slows down the winds, diminishes the Coriolis effect, and essentially the pressure gradient dominates. And we end up with clockwise divergent flow and counterclockwise convergent flow. Understanding all these diagrams is going to help you better understand the global wind patterns that we're going to cover next. Lastly, go check out the animations that I've put on our website right below this video clip. In particular, you're now ready to watch the wind pattern development animation that I've posted and that is also available in the Mastering Geography study area. There's a lot of new material in this video clip. I encourage you to watch part of it again and perhaps go and watch all the animations again, especially the one on wind pattern development that's available in the Mastering Geography study area and on our website. A solid understanding of wind direction will help you understand the rest of the material in this week's lesson.